Okay, yeah.
Yeah, perfect.
Okay, everybody, thanks for coming. Today we're going to have a presentation from Professor Francisco Ibanez. And like you mentioned earlier, I have a muy madrileño accent, so I'm pronouncing her name Spanish and Argentinian. And he's basically going to talk to us today about how interrelated computer science, math, and economics is. So he's a professor, thank you. So he's a professor of computer science, but he loves economics. And so he's going to show us how all three fields are basically interrelated and how you can use computer science and math to solve real world problems in economics. So I'll let you take it from here and get us started. Thank you.
Thank you very much. Hello. I am going to talk about decision making with linear programming. I am currently working at the computer science department in San Juan, Argentina, which is right there. Our main industry is wine, and it's relevant to this talk because in one last part of the talk I'm going to talk about integer programming with applied to wine supply chain. And first of all, I want to thank Dr. Coll for inviting me here. And this was a paper presented at a conference that I presented 3 years ago in San Francisco. So I'm going to present it in a nutshell, not very extensive. And this is going to be actually the second part of the presentation. The first part of the presentation, I'm going to talk about decision making with linear programming. And first I'm going to talk about decision making in general, just a very brief introduction, and then I'm going to talk about linear programming in particular. About linear programming, we're going to start with a real problem, a simplified version of the real problem. Then we're going to explain the mathematical model, the formulation of the mathematical model. Then we're going to solve it mathematically, and we're going to see the implementation in a programming language, actually more than one programming language. Then we're going to look closer to the outcome of the program, and we are going to express this result not only mathematically, but also in the terms of the business world, in such a way that businessmen can understand this result and they can take the action, like for example advertising a certain product or whatever, so they can fulfill their objectives, that in most of the cases is earning more money. So, in the last part I'm going to talk about the interrelationship between these components, okay? So let's start from the beginning. Decision making, you can find decision making in many different areas, very different, like engineering, macroeconomic, neuroscience, epigenetica, and business. This is the one that we're going to talk about now. And when you talk about business, there are two main branches. One is when you have to choose only one choice. For example, you have two airlines, and then the airlines have to choose between two possibilities, maybe more, to sell high price or lower price, but only one choice. And another branch is a combination of choices, like for example, you want to install solar energy in a field, and then you have one choice which is to use solar panel and another one photovoltaic cell. And when you run the program, the optimal solution is, for example, 33.5% this option and the rest this option, okay? So you get actually a combination, not only one choice. And in this case, you can use nonlinear equation, or you can use linear equation, which is the case that we are going to talk about now. And if it's linear, you have integer programming that deals with integer numbers. This is what we are going to see in the second part of the presentation with wine supply chain. And linear programming that deals with real numbers, in this case. And I'm going to talk right now about decision making with linear programming. So this is the topic we're going to start. So decision making with linear programming. So we're going to start with a real problem, and what we want to do is to manufacture labels, and in order to manufacture labels you use a printer machine and a cutting machine. So you introduce the paper, then you get the printed version, and then passing through the cutting machine you get the label ready, okay? And you have a company that produces and sells printer and cutting machines. So the company that sells this machine, we are going to start assuming that the selling price is 1 million each, and in order to produce X quantity of printer, you need X quantity of containers with material for printer and X quantity of group of people. And similarly for the cutting machine. And you have availability, you have only 6 containers with material for printer, and you have only 6 containers for cutting, and you have only 10 group of people. So the problem that we want to solve is the following: how many printers and how many cutters maximize the revenue, where in this case the revenue is simply X plus Y. When the prices are different, you are going to change this function. So this is what we want to maximize, and we start with the mathematical formulation. The mathematical formulation in this case is very simple. It's just maximize X plus Y subject to these 3 constraints. Okay? So now we are going to go to the mathematical solution. We are going to solve it. So we're going to start a graph, and then we take the first constraint. If we take X equals 6, you have this line. If you have less or equal, you have this semi-space. Similarly for this constraint. And then this equation with equal is this, and less or equal is this space. So this green area, that's called a solution space, because it's where we are going to find the solution. And you have the objective function that in this case when you want to maximize. And these are the constraints. So this is the shape that represents the constraint. What is the shape? How can we graphic the objective function? Well, the objective function has this shape. So if you see this figure from above, you are going to see, you see it from above, you are going to see the solution space. Correct? So here you find one optimum, which is in the point 4,6, that in 2 dimensions is there, 4,6. And then if you plug in 4,6 in the objective function, then you get one optimum, which is the value 10. Here you have another optimum, in this case is this point, which is 6,4. 6,4. So if you plug 6,4, you have another optimum, which is also 10. And actually, in all of these points, that in 2 dimensions, all of these points, you have the value 10. Okay, so you have infinite value for the optimum. Now let's talk about the real problem, and this is more realistic, that the price don't have to be equal. So let's say that the selling price are 3 and 2. In this case, how the mathematical formulation of the model changes? Well, the objective function is going to change, it's going to be this, okay? So how the mathematical solution changes? Well, if we take a closer look to the mathematical solution, this is what is going to happen. So if you see this wall from above, you are going to get this diagonal, okay? So now, if we have this wall, you work from above, you are going to see this line. So in this case, you have infinite optimum, where here you have only one optimum, that in 2 dimensions is this, and we are going to see a little bit more with detail what happens if we change prices or if we change constraint, how this figure is going to change. So, and in order to do that, we're going to use MATLAB, okay? So, there's some doubt up to now? Is kind of clear? Okay, good. So now, this is the starting point, okay? 6, 6, 10, etc. So if we change, let's say, this to the value 3, then this slope that corresponds to X printer is going to triplicate, okay? And if we do the same, let's say with 2 for cutter, this will duplicate. So let's do that. So you get 3, and then you get 2, okay? So now let's try to relate the graphical solution with the mathematical solution with a real problem. You can see here that if we replace the solution, which is 6, 4, and the optimum is 26, we replace this 6 in the first constraint, we have 6 and 6, which means that we are using all of the container for printer. Okay, we're using all of the resources for the first constraint, which is this one. Okay, I have to switch. Okay, so if we replace this 6 here, we have 6, 6, meaning that you are using all of the resources. Here you see that this 6 touches the optimum. Now if we increase this from 6 to 7, then you are going to have more resources, you are going to produce more things, and then the optimum, which is 26, is going to increase. Okay? So we do that, and then we see how this 26 increases. Okay? We do it again, and we see how it increases. Okay? Now, if you replace these 2 here, you have 2 less or equal than 6. It means that they are 2 and 6. There are 4 containers for cutter that you are not using. So if you have extra money because the company, you know, make enough money, and you want to buy containers, you are not going to buy cutter container, because if you, let's say, increase this value from 6 to 7, instead of having 4 extra not used container, you are going to have 1 more. Okay, and then you will see that that this 28 doesn't change. Okay, so if you see graphically, what you are doing is expanding this wall. Okay, so if you increase from 7 to 8, actually what is going to happen is that you are going to fill up this gap. But as it's not touching the objective function, they will have no effect. So it will be more inventory, more money, okay? So if we go to this 8, okay, again, you see, okay, you see that. And the same thing happen if you change this. If you change this from 10 to 11, 10, if you see it from above, it is a diagonal. Okay, then if you increase to 11, then this line will move up, and then you have 8 and 2, 8 plus 2, 10 here. 8 plus 2, 10. So you are using all of the personnel, okay? All of the group of people. If you increase in 1, then the solution space will increases, and then this wall will move outward, and then you are going to increase the optimum, okay? So let's do it. So it's kind of similar, okay? So if you increase more, you will see that this wall expands outward, and then this line is like the constraint budget that you have in macroeconomic, when you have in different curves, and you have the constraint value, you know, that if you increase this value, you know, so if you increase this value, okay, and now this, the the optimum is 32, which is this. Okay, you can see here the 32, right? And if you see this from above, then this wall will be converted in this line. Okay. Okay. So let's back to the PowerPoint.
I just have a question. Does everybody know what MATLAB is?
Sorry.
I was just asking if everybody knows what MATLAB is.
Ah,
Anybody know?
no.
Let's talk about what MATLAB is.
Basically, well, I love it because it's quite easy at the beginning, maybe a little different compared to C++, Java, the conventional language, but then as you get used to it, it's quite friendly, and you can draw all of this thing, which is cool.
It's a computer program.
Yeah, with a lot of math and okay, so we have seen the mathematical solution graphically, but normally we want to find analytically. And so if this is the model, this is the objective function, which is represented by this figure, and these are the constraints that are represented by the solution space. The most common way of solving this analytically is the simplex method. How the simplex method works? Well, you start from 0, 0. So if you plug in 0, 0, the objective function evaluates to 0. And then what you do is to choose the maximum slope. So you have 3 is this slope and 2 this slope, is what we have seen recently. And then what you're going to do is to follow the maximum slope. So you follow this direction, the higher slope, you follow this direction, so you go from 0, x, go from 0 to 6, okay? So then you go from 0 to 6, you evaluate the objective function, which is 3 times 6, 18, which is this value, okay? And then you go on with the other variable, that is y, so you move y, so you follow the periphery, and then, which in 3 dimensions is this. So here, in this point, y take the value 4, so it's not 0 anymore, now it's 4, and now you evaluate again the objective function, and you have 18 plus 8, which is 26, which is this high, okay? So this is basically, in a nutshell, how the simplex method works. It's actually more complicated than that, but it's just to give a very... So actually what you go is, you go 0, 18, 16, okay? So this is the simple method. So you get that the optimal solution, you find it in x equals 6 and y equals 4, and the optimum is 26, which is the value, okay? So far we have seen the problem, then we have seen the model, and then basically you have two products. In this case are printer and cutter, and then you have the constraint where these parts represent the use, what in order to manufacture, in order to produce this product, you have to use this material, and you have this part which represent, for this case, the availability. And when we formulate the mathematical model, we have to add one important thing that I omitted deliberately at the beginning, which is that x and y are the decision variables. Decision variable means that this is the value that you want to find. And they are real and positive, which is kind of obvious, but for programming it's not that obvious. It's very important. So we solve the mathematical solution graphically and analytically and using the simple method, and now what we are going to do is to show how you program, how you solve this problem using a computer language. So the computer language that we are going to use is OPL, that stands for Optimization Programming Language, and then we're going to take a closer look at it. So this is the program. written in OPL. The environment is quite simple. If somebody is interested in how this works, is quite simple. Well, the part that I'm going to explain is the program itself, which is this part. So the first line, which is the first two lines, which is this, says dvar. Dvar stands for decision variable. Float plus, which means real and positive. Float is real. If you want to know why, you can either ask him or ask me later. The first generation, 40 years ago, they used real in Pascal, this kind of language, and then which the computer science changed it to float. I can explain later why if you want. It's really not relevant. So float, take it as synonym of real. So here I'm saying that x is the decision variable and is real and positive, and the same with y. And then the rest is straightforward. You just have the objective function and the constraint. Okay? So when you run this program, then what you get is this, exactly this, which of course coincides with the analytic solution and with the same the graphic solution. So now we're going to get a closer look at the real problem. Then you say, what if the real problem, let's say, is bakery and the product are this, or the real problem is painting, and then the product is product one. The prices are going to change quite possibly, and these coefficients are going to change as well. So let's change it. And then they say that the product one is painting for exterior, and the product two is painting for interior, two different kinds of painting. And then they use this material. So the mathematical model, the structure of the mathematical model is going to be exactly the same. The only difference is that this value are going to change, but the structure is going to be exactly the same. And the program, the structure of the program is going to be exactly the same. Only this number will change. Okay? So you can use the same methodology for different kind of real problems. In this case, because we change this number, the solution is going to be different. It's going to be 5, 3, and the objective function is going to be 45, which is this height. Okay. This is the program written in OPL. What other language can you use to write the same mathematical model? Well, now we're going to see a program. You can use Excel. With Excel is possible, kind of tedious, but it's possible to do it. It depends. If you are used to Excel, it's easy. Otherwise, it takes a time. You can use also WinQSB, which is even easier than Excel. It's just a form that you plug in the coefficients. So you take 3 and 10, and then this number, you just fill number like in Excel, and then you specify that you want to maximize, and then you just press an icon, and then you get not only the analytical solution but also the graphical solution. So you get this, which is quite similar to this. Okay. Then you can use MATLAB. In this case, analytically, it's kind of more complicated if you don't know MATLAB. But the advantage is that with MATLAB, you not only get the analytical solution, but also you get the graphical solution. Not only in 2D, like WinQSB, but also you can have this kind of graphic that is actually the graphic that I used recently with MATLAB. So it's okay. So you have in one extreme WinQSB, which is very simple but very limited, and in the other extreme MATLAB, which is very powerful, but you have to pay the price. It's a little bit more complicated to program. And then in the middle, you have Excel, you have OPL, and you have actually many. So So far, we have seen the real problem, the mathematical solution, and the implementation. Okay, we have seen these three modules. So now we are going to talk about the interrelationship between these modules. Firstly, we have used a simplified version of the problem. So what are the main advantages of this simplified version? Well, it's good as an introduction. It's useful to study mathematical solution and implementation. So you can compare languages. And you have the present feeling that we are understanding this, which is a nice advantage. What is the main disadvantage? Well, that in the previous example, we have seen actually simplification of the real problem. For example, this point, I deliberately choose integer numbers, so it's easier to show, you know. But what happens if the solution are not integer numbers? What is the size of the real problem is much bigger? You have, say, 20 variables, you know, 15 constraints. What if the objective function is not linear? Okay? Well, so now we're going to do is to go from simplified problem to real problems. So we're going to see decision making taken from this book, which is a real problem. And what you're going to do is to pass from conventional energy to solar energy. And in the previous example, we wanted to maximize revenue. Now we want to buy solar panel or photovoltaic cells, so what we want to do is minimize cost. Before we have product one was exterior painted. Now we have an option one, it's not a product, which is solar panel, and before we have interior painting, and now we have another option, which is photovoltaic cell. And before we have materials or resources, and you have availability for these resources. Now we are going to have criteria, and you are going to have threshold. So what are the criteria in this case? Well, the piece of land, the surface that you're going to use, the efficiency index, the financial index, which is the return on investment, and the generated electric index. So here you have less or equal, exactly like we had before. So here you are saying that you cannot use more land than this threshold because this is the surface that you have. Okay, it's bounded. You don't have infinite land. Then you have greater or equal, saying like in this case you have as a minimum this return on investment. If it is more, better, but at least this return on investment. So you have upper bound and lower bound. So if you represent X solar panel and Y photovoltaic cells, these constraints are very similar to the constraint that we have seen before. So what we have is something like, this first constraint is something like that. This second constraint is something like that. So up to now, the solution space will be like this, okay? It's exactly like before. And now we have this constraint. So now it's going to be this shape, okay? Because it's greater or equal. So the solution space up to now will be this. And then the last one, generated energy, something like this. So the solution space is going to be this, okay? Before we wanted to sell machines. So these were the selling price, okay? Now we want to buy. Therefore, we want to minimize cost. So this is the objective function that we want to not maximize but minimize in this case. When in the previous problem, when you maximize revenue, what you do, another graphical way of analyzing the solution, is start with a slope determined by what? Determined by the coefficient of the objective function, okay? And then you go down until you touch the solution space. And this is the maximum that we were looking for here, in this case, okay? Now we want to minimize. So what we do is start with a parallel line with a slope determined by this coefficient, and now you're going to move up until you touch the solution space, and this is the minimum that you're looking for, okay? How the program changes. Well, if we use OPL, then instead of having maximize, you have to write minimize, and then the rest is straightforward. The only difference is that now you have to put here greater or equal, but the structure of the program is the same. So the nature of the problem is quite different, but the solution, the program is quite similar actually. Okay, and now I'm going to talk about the second part of the talk, which is more complicated because it's a real problem. It's a more complicated real problem. And in this case, we're going to use integer programming in the Y supply chain. This part is going to be a little bit more complicated because I'm going to explain very fast. However, you have the videos, which is like half an hour or something like that, they are in YouTube. So if you, this is my page, Economic with Francisco. I am Francisco, like the Pope. He's from Argentina too. So here, if you enter in this page, you will see a video like this. Actually, this video. Okay, so you can see with more detail. So now we are going to just explaining. We are going to focus on the integer programming part, only this part. So this is the title of the paper. So now I'm going to show you very briefly the description of the problem. So what you have to do is to schedule harvest and loading in farms first. Then you go with the truck. The second activity is transportation from the farm to the winery. And then in the winery you do uploading and crushing. And finally transport with the empty truck back to the farm. Well, it is possible to use the same truck. This is not extremely relevant, so it means that when you come back with the empty truck, you can go to another farm, different farm, and then perform the other activities. There are different types of trucks. You have dump truck, normal truck, and big truck. And there is a constraint that the solution should meet this condition, because these are the quantity of truck that you have in the winery. So you want to use the truck of the winery, and then to hire it from outside. So we call this the quantity of truck constraint. So these are the activities. All of these green activities are harvest and loading in farms, and they have to be scheduled in this temporal window, because in Argentina the picker takes 2 hours to rest. And the normal truck loads 15 tons and the big truck loads 30 tons. And then there are rules for the duration of the first activity that is not relevant to integer programming, so we don't need to explain this. Duration for the transport and duration for the unloading and crashing that it is relevant now. So this duration depends basically on the type of track, which means if the track is big, it's going to take longer. So the main objective is that for the dump track, I am showing a solution. There are these 4 activities that are performed by this kind of track. Then these 3 activities that are performed by the normal track, and these 5 activities that are performed by this track. So the different track load different kind of time. So what you want to do is to maximize the quantity of time, the quantity of time crashed in the winery. Okay, this is what you want to maximize. Subjective to the constraint that all of these activities have to fit within this temporal window, which is the time in which the winery is open, which is from 10 a.m. to 10 p.m. Okay? Then there are secondary objectives that you can see it in detail in YouTube, but we are going to explain it very fast because it's not too relevant to integer programming, which is to reduce track if possible, reduce total track consumption, which is related to environmental issues from the economic point of view, to externalities, okay? And well, here you have kind of complicated function, but we don't need to talk about that now. And then to reduce the weight of track, because the track normally weight in the farm, that in Argentina they take advantage to have mate, you know mate? Everybody in Argentina is mate. You know? So even our Pope, mate is from Argentina. And also the weight, not only in the farm but also in the winery, that people take advantage to take siesta. And then we want to reduce this. This is another secondary objective to fulfill. So now we're going to jump directly to the implementation, especially the part implementation. Use OPL have the power that you can use different engines. For example, you can use linear programming or integer programming, constraint programming, scheduling, and then you can pass data from one module to the other. Okay? So actually what we are going to do now is to, here you use this CP that stands for constraint programming, that is one engine that you are going to use, and then integer programming, which is the other engine that you use. So you find the solution with one engine. Engine is basically a big program, okay? So you find the solution with one engine, and then you pass the solution to the other module, and then you work, okay? You can, this is a big advantage that you have with OPL. You cannot do that, for example, with Excel, with Win USB, or this kind of program. So now I am not going to focus on this part, which is kind of complicated, but you can look at that in the YouTube, in the video. I am going to be focused on the integer programming part. So we have one dump track, and here you have these 4 activities. I am using the optimal solution to explain how I program. Okay, so once you find the optimal solution, and then OPL allows you to print this Gantt, it's called Gantt graph, okay? So this Gantt is actually, you get it in OPL. Then I am using the optimal solution to explain how you program in OPL. So here you have 4 activities performed by the dump track, 4, and this track load 10 tons, and the duration of this activity is half an hour, 30 minutes. Then you have the normal track, and you have 1, 2, 3. 3 activities performed by the normal track that load 15 tons and have this duration, and 1, 2, 3, 4, 5 activity performed by the big track that load 30 tons and last 1 hour and a half. So you want to maximize the quantity of tons subject to the quantity of track constraint that we have seen before, and subjected to temporal constraint, which means that all of the activity have to fit within this temporal window. So how do you program in OPL this objective? Well, all of these activities have to fit within this temporal window. This is the temporal constraint. And now we're going to see how you program that in OPL. Well, this part of the program is a little tedious because we have to deal with database, take from data from one part, you know. But what I have done is to do a simplification. I remove all of the database thing and I put just numbers so you can see easily. So this is the solution written in OPL. So here we are saying that these 3 variables are the decision variables. So actually we don't know these numbers, 4, 3, and 5. This is what we want to find. We want to find the optimal solution. We want to find these numbers that make the quantity of time maximum. Okay? So these 3 numbers we don't know, we want to find them. So what we do is to say that we want to maximize the quantity of DAM activities time the ton, because we want to maximize the tons. Time 10 plus the decision variable that we use for this track, time the quantity of ton, which is 15, plus the quantity of the big track, time 30, and this is what we're going to maximize. Okay? So this is the total amount of ton that are going to be crushed in the winery, and this is what we're going to maximize. Subjected to quantity of constraint, which is the constraint that we set at the beginning, and subjected to the temporal constraint, that means that the activity has to fit in this temporal window. So how do you express the last constraint? Well, you say that the quantity of activities performed by the dump track times the duration, so this times this, which is the variable that we don't know, we have to find, times 30, plus this decision variable, I can see, this decision variable, okay, time the duration, which is 50, this decision variable time 50, plus this decision variable that we don't know, doesn't obey me. Okay, this decision variable that we don't know, time the duration. Okay, so what we are saying is that all of these activities have to fit without this temporal window. And this temporal window goes from 10 a.m. to 10 p.m. So it's I can see from 10 a.m. to 10 p.m. So you have 12 hours, but everything is expressed in minutes. So you have to multiply times 60. So this is the program. And then some details that if we run this program exactly like the linear programming program that we ran before, writing the var float plus, then we will find real solutions. Okay, and we don't want real solution. We want, in this case, integer solution. We want to know. So the program is going to say that this variable is a decision variable, but is integer, not real. So with this int or float, you decide whether you are talking about linear programming, which you use real, or integer programming that use int. Okay? And that's it. This is the program. When you run this program, you get this solution, which is 4, 3, and 5. So you find the optimal solution. Okay. Well, and the second part is quite complicated because it's related to the secondary constraint, and then in this part you use the other engine, which is constraint programming, but you can find this detail in the in YouTube. Okay. Okay, so questions? Actually, it was less than I think I went too fast, but it was 40 minutes. Ah, yeah, I think it was faster. Okay. Okay, question time. Do you understand? I start with the first question. You understand? Yeah.
What computer language would you say helps the best when it comes to economics, or it goes along with it the best? Is most when you're trying to get to.
Well, it's a very relevant question because can you raise your hand the one that study economic or involved in economic? Then computer. And math. Okay, so computer math. Okay. Well, I would say MATLAB because although OPL you use, I can give you a rough idea very quickly what kind of thing.
Don't start with MATLAB.
Sorry?
It shouldn't start with MATLAB.
Yeah. Actually, you can use a lot of things. I will give you.
Because they need linear algebra first to understand. You need linear algebra to understand MATLAB.
Well, normally people think about linear algebra, but actually it's much bigger. I mean, you can do, because the advantage of MATLAB is that you can incorporate not only program, but many people program, let's say, schedules problem, and network, genetic algorithm, well, many things, and then they incorporate for free this library. So you can import this library and then you can do so many things. But to give you an idea what kind of thing you can do with MATLAB, for example, you can find this in, let me close this. For example, what do we have here? Here, for example, let's some little example about, let's say, micro, macro, econometry, let's say, and finance, a little bit of So for example, if you have macro, how many of you have seen macroeconomic? Raise your hand. Huh? So you are familiarized with macroeconomic. Oh, sorry, this is a micro. So here, for example, this is a typical problem, but it is I'm going to start with this one, okay? And macroeconomic, okay? So for example here, you have you represent the goods and services market, the money market, exchange market, etc. And then you want to do things like, for example, increasing government expenditure, reducing taxes, increase, and then you want to see the impact, how the interest rate changes. For example, if you use fiscal policy, the interest rate is supposed to go up. If you use monetary policy, expansionary monetary policy, the interest rate is supposed to go down. And then you can simulate this thing. For example, you say, I increase government expenditure, and then I see that the I see how the interest rate goes up, and then you have an increase in GDP, and you increase inflation, and then by changing the coefficient, you understand, and then if you want to see the causality of this event, and then you want to see how investment changes, how the exchange rate changes, you can, for example, do things like you can do things like, for example, go step by step, and then let's change, let's say, money market, and then you can see the causality, you can see the equation, and then you can understand how this curve shifts one by one. Here actually is prepared for the different side, but which is kind of easy accommodated, but it takes a little time. So if you go step by step, you can understand how, for example, this is easy to explain. Because you use expansive monetary policy, the interest rate goes down, which is not trivial to explain in 5 minutes, but in YouTube you have the very, very detailed explanation. So for example, because when you lower the interest, you incentive company to invest more. So if the interest goes down, the level of investment is going to increase. So then you justify this, and then if you change the interest in your country, okay, then you can see this is something that is kind of easy to show. Then here we are talking about Argentina, okay? So if you lower the interest in your country, then the equilibrium that you have before is going to change. How is it going to change? Well, the interest in your country is lower, so it's better to do this, to buy dollars, go to the state, put the money in the state, and then to go like this. And then you will have demand of dollar. When the demand increases, then the exchange rate is going to increase, okay? So then you will have this value approximately, and then you go step by step, okay? and then how this is going to change. Okay, the aggregate demand is going to shift, and then you can analyze whether it's going to shift parallel or not. All of this kind of thing, and then the other thing that you can change the coefficient. Let's say maximum propensity to consume, sensitivity of investments respect to interest rate, all of these things, and then you can see the effectiveness of the policies. Okay, so for example, if the current situation in Argentina, that people are very scared because we are not in the boom, so people don't invest. So the sensitivity of investment with respect to interest rate is very low. So even lowering a lot the interest rate, people are not enthusiastic to invest. So you change this coefficient, and then you see that the slope of this curve change. In particular, if the sensitivity of investment in terms of interest rate is too low, let's say 0, this is going to be vertical. So you have absolutely no effect by using a monetary expansion. Okay.
So learn MATLAB, but learn MATLAB probably after you've learned something.
Yeah, it takes some time to do this thing with MATLAB. And for example, in micro, you can do things like, for example, all of this that I explained in a nutshell. You can see with a lot of detail. The videos are more than, I don't know, like 200 hours of videos, so you can see slowly, step by step. So, for example, to show you a very, very fast thing about micro, for example, programs, for example, economy. Well, that's going to be maybe interesting for mathematicians, because sometimes micro,
And Franklin, too, the program you want to learn depends on what you want to do, right? So you have to figure out if you want to go to grad school or do you want to work in the private sector. And that'll help you. And then if you just like programs, learn them all, right? So just start with R. And I would just do R if you know you don't maybe want to go in the private sector. If you go in the private sector, a lot of times those companies want you to know like SAS, SPSS, and STATA. And then if you do other stuff, then they're going to want you to know R, MATLAB, stuff like that.
yeah, now actually it's more and more common to use in the private sector, because at the beginning it was kind of academic MATLAB, and now they are more and more incorporate MATLAB in the private sector. Okay, for example, well, this is the typical thing that you have in different curves. You have a function. Here, for example, you have the very well known in economic, I don't know if you're familiar with that, the Coll-Douglas function, that actually they use it in microeconomics, but also they use it in, if you divide macroeconomic in the short run, medium run, and long run. They use it in the long run for growing. You know, it's very well known in economic expansion. And then you see, for example, that in this case, what we want to find is this is the function that we want to maximize, subjective to this constraint, which is basically the money that you have to invest, and these are the prices. So this is what is called budget constraint, line constraint. You have to, depending on the bibliography, different names. And in this case, is 45 degrees because the prices are the same. Okay, and then if you want to see the graphical representation, this is the graphical representation of the Coll function. So actually, this, which is 2D, if you want to see in 3D, you see the vertical plane, which is this. So what you want to find is this point. So then this can help you to understand things that at the beginning can be kind of complicated if you are not familiar with mathematics. Just for example, if you increase the exponent of, let's say, the good one, well, good one, it's in Spanish. So for example, you increase this, let's say to 7, and then this part will grow faster than this part, okay? So then the solution will change, okay? The solution will change. And then, for example, if you increase this value, which is a technological constraint, it means that, for example, you have labor and capital, you can increase the GDP without touching quantity of labor and capital by increasing technology, okay? It's a machine more powerful, whatever. Then what is going to happen is like a poppy that you know? So it's going to give, and here, for example, this is the indifferent curves, which means, let's assume that you have this height, and then all of these points have the same height, okay? And this is the indifferent curves that correspond to the optimum, right? So here is cool because you can relate the concept of gradient, which is, well, for mathematicians, it's very clear. This is a vector that indicates in which direction you are in the mountain, in which direction you have the higher slope, okay? And in mathematical terms, it's partial derivative, okay? And then you can relate this with the marginal substitution, you know, that you study in microeconomics. So, for example, if you increase this to 9, this is not going to change at all. It's going to be exactly the same. What is going to grow is the gradient and the partial derivative, because actually what you get is the mountain with more slope. And the gradient is measuring actually two things. One is the direction in which I climb faster, maximum slope. But also the magnitude is telling you with what slope I grow. So the direction tells you in which direction, let's say north, and the magnitude is telling you how high, okay? So if we increase this, we will see that this goes like this, okay? And this will enlarge, okay? So this kind of thing are kind of difficult, and in different cases is exactly the same. If we change these things, for example, let's say the price is 2, then with $10 million, I use it only for good one, and then you know that it has passed through here because I use the $10 million here. If the good one costs 1 million. If we increase it from 1 million to 2 million, then with $10 million you're going to buy only 5. So this will go like this, okay? And then this wall is going to turn, and then the solution is going to be different, okay? And then the solution in the case is 3 point blah blah. If you go this with 3, then this will be up to the third, roughly here, okay? And then if you increase, let's say, the budget, when you have more money, then this line will shift out and this wall will shift out, okay? So, and the optimum is going to increase. So here, instead of having instead of being this solution, the solution is going to be bigger number, and here you will have, so let's say here, okay? So it shifts out, and then you will see that this 3.46 is going to increase, okay? So these kind of things, and from the private sector especially, one of the main things that you use in MATLAB, use it for econometric, which is a very cool subject because it's related math, statistic, and economic. Everything goes together. So you can do, interesting things, like for example.
And I'm just gonna say, in the interest of time, does anybody else have any last questions? If not, we're gonna let students eat, because I know.
Sorry, if there's
we're gonna
some.
have to go to another class in about 10 minutes too. And then we're gonna let you ask some questions privately too. Anybody have any questions?
Yeah, even if it is necessary, I mean, I might spend another day. I mean, it's not part of the plan, but if I have to do it, or we can communicate by email.
Yeah, so we're gonna say thanks again. Because some people are gonna have to go to another class, so we're gonna let them go ahead and get some food and drinks and eat, and then ask questions. He's still here, he can show them some more stuff as well.
Yeah, you will have some other question. I'm pleased to answer. Yeah.
Very good demonstration of linear programming. Probably the best I've seen.
Oh,
Yeah,
thank you
it
very
was
much.
great, it was great, but I know students want to eat because some of them are gonna have to go to another class. Because this class ends at 3:20, so I want to give them time to eat and kind of talk to you one-on-one. So that's the only reason why I'm ending
The
it.
relevant thing that I haven't given is my email address that Tracy has it. So if you want to, thank you. If
You're
you,
gonna talk to them at 3:30.
okay. So if somebody want to contact me, here is my email, so we can, and through the page.
And you can talk to him further until my next class starts. And you can
Oh, yeah.
go to class. So feel free to come eat and talk. And I know you're probably hungry, so. And you might have to leave, so come on in.
Okay, so maybe. Mira, shall we, Tracy, shall we turn off the yeah. Bye. From Argentina.